Hello everybody. So where are we? Okay, so we are going to discuss a very important concept of computability theory, which is known as non-determinism. So basically, I'm going to discuss chapter number 5.1, which is non-deterministic Turing machines. Now, this is part of non-determinism, and we have very interesting chapter inside it called P versus NP, and the most uh, discussed problem of the century. And basically, this P versus NP is a problem which has been declared unsolved, and if one can solve this problem, you will get $1 million worth of bucks, and which has been announced by the Clay Mathematical Institute. So basically, this is one of the 7 millennium unsolved problems, and as you know already, one problem is solved by Gregory Perelman, that is Frontier conjecture. But unfortunately, Perelman has declined the prize. But anyway, you people can try for solving this problem P versus NP. Now, that is one of our later sessions will cover in detail, and that will be very interesting, in fact. So, so we have covered the theory of computation and complexity, and we have covered the deterministic Turing machine as well, and we have also seen the construction of languages and how languages are accepted in machines, and how do they behave, what are the grammars of those languages, etc. We have briefly discussed, but all those probably may not have given you much of interest. But this chapter number 5 and chapter number 6, which deals with probabilistic algorithmic theory, these will give you much more interest than you have already got. Anyway, so what is non-determinism? Now, non-determinism as simply is something which is not determined in a particular way. And what is non-deterministic Turing machine? Non-deterministic Turing machines are machines which can go to its next state with different choices. In contrast to deterministic Turing machine, Q0, the initial state of non-deterministic Turing machine, can go to Q1 or Q2 or Q3 or whatever. But in a deterministic Turing machine, Q0 goes to Q1, maybe in a unique way. There is no other alternative that it can take. So it's kind of unidirectional, starting from its root. So if we think of this concept as a tree, then the initial state can be thought of as a root, and all other state can be thought of other branches of a tree. So there will be many branches in a tree. So this machine configuration from root to other branches will be choice of the algorithm. Okay, so it can, at one point it can stop, and what we call the machine is halted, and at one point it may not stop, so the machine has not halted and it is continuing in a loop. There may be branches in this tree where the machine is always in a favorable way, which means always positive. So which means in this branch always we go to yes, 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 which means we accept the input. There may be a possibility in some branch where there it is rejected, which means it's not in our favor. So this is not the result is the result which is coming out is not desired. So it may be a no, 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 etc. So this is a reject state. So from root it can go to three states traversing different branches. One may be an acceptance state, one may be a rejection state, and one may be the loop state. So this is the idea of non-deterministic Turing machine and its behavior. Now what is the mathematical function which works for non-deterministic Turing machine? The mathematical function that works here is delta q cross gamma map to power of q cross gamma cross left comma right. So only difference is that this power from a deterministic Turing machine. This power means set of all subsets, which means 2 to the power q cross gamma cross left comma right. So we are considering all possible choices that a machine configuration can take while computing. Now what is its utility? The utility of non-deterministic Turing machine is to understand different types of computability problems where we have kind of multi-processing or say parallel processing, or maybe if we just consider a kind of realistic problems, which is, let's say, traveling salesman's problem, where we want the salesman to travel different cities only once and come back to the original city with the optimum expense. So how to solve this problem, or whether this problem is solvable or not, this needs to be simulated in a non-deterministic Turing machine. Also we have, if you consider say operating systems where there are a lot of parallel processing goes on. So before creating an operating system, one needs to, a computer scientist needs to really evaluate its feasibility, its utility, whether it's doable or not, if it is doable, in which time it is doable, what is the cost of doing it. I'm not saying dollar, it's the cost of say time and space. So all these actually we need to understand. We need, suppose in quantum computing. So how powerful the quantum computing may be. We are making quantum computer, and we need to understand what kind of problem it can solve, or what kind of problem it cannot solve, or what kind of problem it can solve within a finite time, and what kind of problem it can solve within infinite time, and what kind of solutions will be useful for human beings. Okay, so all these needs to be understood before we delve into doing things or doing real life projects. So making an operating system without understanding this doesn't make sense. Making a new machine with some power, where it may happen that the machine does not satisfy us with time complexity in order to solve the problems. So that is why we need to understand beforehand what is to be done in a non-deterministic Turing machine, so that we can understand the consequence of a particular problem. This is what is all about this non-deterministic Turing machines. Now we will prove some theorems in this class. The first interesting theorem in this class will be to prove that every deterministic Turing machine is also a non-deterministic Turing machine. So in order to prove this, okay, we will prove it sometime later. But what we are going to say about by this, that is very important. Now you may have a question in mind. So what is the use of deterministic and non-deterministic Turing machines, whether if they can do everything same, whether they are powerful, less powerful, etc., etc., etc. So all these questions we will discuss, and definitely you will get your answers. In order to get the answers, we need to prove some theorems, and we will prove these theorems in our later classes. So first tell me whether you have understood this prelude of going for non-determinism to be a concept which needs to be understood through non-deterministic Turing machines. Thank you very much.